Good morning, everyone, and welcome to today's Autodesk Virtual Academy session. I'm Nigel Mbayak, Application Engineer here at KETIV, and your host for today and all days. Today, I'm joined by Nikhil Venkat. So he's an application engineer here on our team, mainly working with our post-sales team, doing a lot of data management stuff. But where he really shines is in simulation, both in mechanical simulation and CFD, right? But today, we're going to be going into Nastran In-CAD. If you don't already know, those of you who do have the product design and manufacturing collection already own Nastran In-CAD. So that might be a tool that you might have access to, but you don't have it installed yet. If you wonder if you do have it or not, you have some questions on how to get that on your machine, definitely reach out to us, let us know, and I'll make sure that I get one of my teammates, to help you get that on your system as soon as possible. Today, Nikhil's going to be talking about element types in Nastran In-CAD. So one of the options in any finite element software, just about any finite element software, are the types of elements you use. Nikhil's going to go over the different types of elements, what kind of use cases you use them for, and just how to get the most accurate results by using, the right elements at the right time.
So first of all, I just want to talk about myself a little bit. I am an applications engineer here at KETIV. I'm the newest member of the team here, so I've only been here a few weeks. I'm from Bangalore, India, Silicon Valley. And in 2014, I moved to Florida to pursue a master's degree at the University of Florida, just so nobody gets us confused with that other school there. I'm new to KETIV, but I have been in the industry for a while, about a couple of years. My focus has been simulation throughout, and I'm a certified Autodesk simulation expert. So as Nigel mentioned, we're going to talk about element types today in Nastran In-CAD. And this is just a quick outline, just a little bit of an introduction on what element types, what elements are in general, why we need them, why we use them, the types of different elements that we have in Nastran In-CAD, how the program perceives these elements and puts them together into what they call idealizations. And then we'll do a couple of quick demonstrations and then wrap that up with a summary and a quick Q&A session. Now, most of us are aware of the traditional product development process: marketing, designing, testing, validation, production. The concept of simulation in general is meant to shorten the testing phase. It allows you to explore design options early in the design cycle before expensive prototypes are created and tested. Now, in order to create and calculate and compute displacements and stresses and strains, or any other results that may be of interest, the FEA process, the finite element analysis process, can be used to obtain these desired results. So the process begins by breaking down your CAD model into small building blocks, into a series of finite elements. And these, as you can see here, are the elements. Now, Nastran In-CAD is going to take this CAD geometry for you, and it can create a mesh. A mesh is just an interlocking of these elements, a mesh for you. Now, these elements are connected to each other at points called nodes. And it is at these nodes that the loads and constraints of any kind, whether they be structural or thermal, it's at these nodes that they get applied. Now, why is there such a big focus on elements and mesh? Why is the type of mesh and the size of mesh important? Now, this little plot shows the effect of the mesh on the von Mises stress at an area of stress concentration. Now, mesh number 3 has considerably more elements than mesh number 1. And as we can see, the change in the value in the actual final result is sizable, because especially between mesh 1, when you look from mesh 1 to mesh 3, it's almost double. And this is because the number of points that are present to, 1, represent the geometry, and 2, to calculate these results at these points of stress concentration, these areas of stress concentration, has greatly increased from mesh 1 to mesh 3. Now, in general, as a general rule of thumb, a higher element count is going to lead to greater solution accuracy. In most problems, however, refining the mesh beyond a certain point leads to very small, if any, changes in solution. This convergence is one of the primary means of actually verifying the results of an FEA study, and we'll look at that in short. You can control the mesh to lead to convergence by reducing the element size and, in conjunction, monitoring the changes in the results. Now, models with certain complex elements tend to converge with smaller element count than others, but the time and resources associated with these complex problems may sometimes be prohibitive. So most FEA studies, at the end of the day, require you, the analyst, to strike a fine balance between analysis time, the cost to run the analysis, and the desired accuracy. Now let's look at the different types of finite elements that we have in Nastran In-CAD. Now the simplest element is a line made of 2 nodes. It's called a 1D element. There are 3 types of line elements supported by Nastran In-CAD: bars, beams, and pipes. And you can also have an axial preload on these elements. Now, to define the geometry or cross section for a beam element is going to require several properties, several cross sectional properties. Now, to input this data, you can either put that in from empirical data, or what's recommended is that you use the inbuilt element library, which has a lot of preset standard sizes that you can just pick, and it's going to populate every property that you need for you. 2D elements are typically surface elements with triangle or quadrilateral shapes as their basic shapes anyway. These surface elements can have either regular shapes or irregular shapes in the model itself. And they're often used for 2D elasticity problems, since they account for plane stresses and plane strains. Now, the fundamental property of a shell element is the actual thickness. You can assign this thickness property to geometric surfaces or geometric solids, depending on what your model requires. Now, 3D elements, or solid elements, are usually used to mesh volumes. Most 3D solid elements only account for translational displacements, and this is something to keep in mind. So the choice of element is very important. When using solid elements, the geometry is entirely described by the geometry of the CAD model. Now, Nastran In-CAD has tetrahedral elements, uses tetrahedral elements, and there are 2 types of those: linear and parabolic. Linear tetrahedrons are mathematically stiff, so it's best to use these only for trend studies where the absolute results are not nearly as important as the relative changes in the results. Parabolic elements are much more suitable and much better general purpose elements that can be used for most applications. Now, Nastran In-CAD terms the mesh itself as an idealization. So essentially, this comes from the fact that we're idealizing the geometry to look like these preset standard elements. Now, for those of you that may have used the software, we can set up different kinds of elements, different materials, doing completely different things, performing differently in the same model. And you just have to create a different idealization for each type. Right? So for a complex model, for example, it can have solid elements. It could have an area that requires shell elements, and it could have components that require beam elements. So you can use all of these in conjunction and the idea is to be able to convert the 3D CAD model into the best possible finite element mesh. Now let's jump into the actual program real quick. And so this is a simple railing, really simple analysis. Now this was created using Inventor frame generators. So this comes in, these beam idealizations are automatically created for us. But if we did want to create a new one, you go into Idealizations, select your type of elements. So for this, we're going to use line elements. So you can select bar, beam, pipe, let's say bar for this one, select a material. And if your material doesn't show up here, you can always add it to the list. Oops, there we go. You can always add it to the list by selecting a material here. So for this one, if we consider, let's say beam 1, and we see that this this structure is represented by a bar element, and the reason we're using a bar element instead of a beam element is that we're not subjecting this to actual bending. So beam elements are allowed to bend, bar elements typically are not. Now for this particularly, since this was used, this was created using frame generator, the properties come in from Inventor. So all your cross-sectional properties are already in here. But if you didn't have that, if you didn't have those properties to begin with, then you can select cross-section, and you have different kinds of dimensions, different shapes that you can use, different channels. So you will have to put in these properties. So I do have an analysis set up already. Right, so I just want to make those visible. Now, our mesh settings here, we're going to use an absolute mesh size of 1. We're going to use parabolic elements because, as we discussed, these are good general purpose elements. Now I can also go into the settings, mess with the tolerances on here. So let's just say I use a tolerance of 0.01. I can generate mesh, and we'll see those different colors. So if I just hid my actual model, this is our mesh of bars and beam elements. And the colors here represent the colors, or they correlate with the colors in your idealizations. So the mesh is quite fine. Loads are applied on the nodes, constraints as well. So that's all we need. We can also add one more load if we like. That's going to be gravitational force. So Fy of minus 386.4. Right, so this here shows you that gravity is acting as well. So we're good to run now. Nastran In-CAD also is really, really quick at solving problems. Now these, notice how your results are in terms of bar stresses, not necessarily in terms of 1 Mises stresses, solid 1 Mises stresses, but this actually behaves now as a series of bars and beams. Now the next model that I have is this little channel here. So I'm going to jump into Nastran In-CAD, and if you're new to the program itself, then the way you would get in from Inventor is it's an environment within Inventor. So just go into the Environments tab and open Nastran In-CAD. So I'm going to use a linear static model for this as well. And notice we don't have an idealization here. So sometimes that can happen. So we want to create one. Right? Now, this is a really thin element. It's a really thin component, rather. So we want to make sure we use shell elements, and this is when you would use them. When you have a thin-walled component that needs a thickness, but you don't necessarily want to be modeling that as a solid. So I can select associated geometry and select different components of the geometry in case I want different elements. But if I don't select this, then these settings are going to be applied to everything, to the complete geometry. So I want to use a thickness of 0.125 inches. And this is just going to be a standard thickness. Hit OK. Oops, hang on. Notice I didn't select the material here, so I'm just going to pick something simple, alloy steel. Right, so there we go. So our material populates here, and we can now select that from the drop-down menu. Now we're going in to actually set this up. So it's going to be fairly simple. I'm going to be selecting edges, fix those two holes there. I also want to apply constraints on this end as well. I want to constrain the motion of these edges and make sure that the only way it's constrained is that it cannot translate in the y direction. I'm also going to apply loads to the same three edges, same side of it. It's going to be an enforced motion, actually. So I'm just going to displace this upwards by 0.01 inches. So now we can go ahead and create a standard mesh, a default mesh. And the way you verify whether your mesh is okay or not is you look at these areas of high stress concentration, right? This doesn't look like a particularly good mesh because the elements that we have here don't exactly represent a circle. So instead, we can go into our mesh settings. I'm going to change my element size to something smaller, 0.10 inches, and update that mesh. Okay, that's slightly better now. We have all of our information in, so we should be good to run.
And just keep note too that I know it seems pretty self-explanatory, but the more elements you have, the smaller you make those elements, the longer it's going to take to calculate this. So you could get like infinitesimally small, but your computer might not be a huge fan of that. The cool thing is we're actually running in-CAD right now on some laptops. We're not even running on like super powerful desktops. So just note that even our not super stellar laptops can run simulation like this. So you don't necessarily need a supercomputer anymore to be able to run advanced analysis.
Yeah. So that was even though we had a fairly fine element mesh, that didn't take very long to run. So Nastran is actually really powerful in that sense. It can also solve a bunch of different element types, problem types. So just as with the 1D elements, where our results were all in terms of bar stress and bar 1 meter stress and bar displacements, here we're looking at the shell itself. So depending on the type of elements you use, the assumptions you make are going to be different, because this is clearly an approximation of the actual physical problem that you're required to solve. So depending on what kind of problem you're solving, what elements you use, the assumptions you make will have to be different, and those assumptions will have to be factored in to your final results as well. Now, one other thing that I did want to show you here is, let me just make these invisible. And one other thing that I wanted to show you was the actual mesh convergence factor. Now, we know this is a good mesh because if you look at the mesh convergence error, the maximum error here is about 0.4%. So that's okay for a solution error. So this is your preliminary way to verify and validate your results from a simulation. Is you look at the mesh and you see if there's anything you can do to actually improve upon the accuracy of those solutions. The last model that I have for you guys is a solid model. This is really simple. It's just it's a regular beam with a hole through one end of it, the loading end of it. So again, this is already in Nastran In-CAD, and this is how the problem comes into Nastran In-CAD from your CAD software. Especially for solids, typically an idealization gets created automatically.
Cool. We'll just fire up Inventor real quick. While he's doing that, I'll answer a couple of questions. While Nikhil blew up his Inventor. Good job, Nikhil. But let's answer a couple of questions here. Can we import assemblies for analysis? Yes. You can import anything from Inventor for analysis. Just curious as to what you need to bring in, if it's the whole assembly per se. And then the second one is, does Nastran In-CAD make use of multi-core capability? Nikhil, can you answer that in about 5 seconds while you're hitting the open on this file?
Multi-core capability, yes and no. That's the 5-second answer.
There you go. Okay.
That's going to require much deeper discussion.
Definitely. So Ian, if you definitely want to talk a little bit about that, being able to use multi-core capabilities on your CPUs, definitely reach out to us and we can take care of that. So Nikhil's got this guy open.
Almost.
Awesome. And so Nikhil mentioned earlier that if you open your Inventor and then you hit that Environments tab, and then you hit Nastran In-CAD from there, if you don't have Nastran In-CAD in that list, it could be one of two things. It could be you haven't installed it, in which case you need to install it, or it's not, the add-in is not loaded. And essentially you just go into your add-ins, there's a big list of checkboxes, and then you just make sure you hit the checkbox for Nastran In-CAD, so that gets loaded.
Okay. So thanks for answering those questions, Nigel.
Yep.
So this is how it comes in. I'm able to click it now, so thank goodness for that. But this is how it comes in. A solid idealization gets created automatically. And if you don't have a material already set up in Inventor, then it comes in as generic. So you'll have to go in and change that material.
But if you do have an Inventor, say you assigned 6061 aluminum to that in Inventor, in your modeling environment, it'll bring it over, which is like kind of awesome.
Yeah. So for this, I'm just going to choose a material. I will pick 6061 aluminum because Nigel seems to like that. So, and the color here is just to represent your actual mesh. So this is a really simple problem, just a very simple bending problem. So I want to fix this end, apply a load on this end, let's say minus 5,000. And minus just represents that it's in the negative y direction. and I'm going to generate a mesh. So look at my settings. I think I can reduce the element size a little bit, turn that to 1.5, generate that mesh again. Right. Now, no matter what I do, though, if you look, actually, let's make this more visible. Green. Right, so if you notice, this still doesn't accurately represent the geometry, the actual geometry. The meshes, there seem to be nodes inside this hole, which is not what we want. So when you have areas of stress concentration like this one, you want to, one of the settings that you want to turn on is go into your mesh settings, hit the settings button, and project mid-side nodes. Just check that box, hit OK, and generate the mesh again. And that suddenly looks a lot better now. So I didn't change anything else. But when you have these areas, holes, fillets, you want to make sure, sharp corners, you want to make sure that you turn on project mid-side nodes. Just a quick tip there. So the rest of it looks good. Should be good to run. Right, so the profile looks exactly like what you would expect. And again, when you look at your final results, all of your results are with respect to an actual volume. So these are all solid stresses and solid strains and solid displacements.
Definitely. Yeah, I know we went over elements today, but something equally as important, if not more important than elements, are the meshes. They're kind of intertwined and related. Elements comprise your mesh, so they're kind of intertwined in that sense. I feel like doing a mesh AVA might be super important because just being able to refine the mesh in a proper way without getting too crazy in terms of like element number, be very valuable. So if anyone thinks that is super valuable as much as I do, definitely make note of that in things like the survey and the questions, and we can make sure to prioritize something like that. I know that when I first started doing simulation, I think, what is that, almost like 6 or 7 years ago, I was just like, man, I've got a really awesome computer. Let me just make the mesh size infinitesimally small and run this thing for like 16 hours. And then you get an answer that's maybe like 0.5% better than the one that took you 30 minutes. It's not worth it. Yeah. So definitely something to keep note of. Where to stop refining your mesh. Yep. At what point you kind of hit that barrier of, you've hit that convergence. Yeah. So definitely keep that in mind. Go ahead, Nikhil.
Yep. And now some of these settings in here, right? The mesh settings, they will require much deeper discussion. So what are mid-side nodes, for example? What's the difference between linear and parabolic element orders? That's probably beyond the scope of this particular AVA, but please reach out to us and we can have that discussion.
Definitely. The mesh table.
The mesh table.
I'm a fan. I'm a big fan of the mesh table.
This is awesome, especially if you have assemblies. The mesh table is awesome because you can edit your meshes and your different kinds of elements and everything inside this one table and keep updating.
Yep, per each different solid. So if you have multi-body, it's like assemblies, it makes it a lot easier.
Yeah,
so
definitely. So we'll jump straight back in here. So just to summarize real quick, elements in mesh affect the accuracy of your FEA solution. They're one of the things that you actually have a lot of control over, so you need to make sure you're choosing right elements, meshing it correctly to actually get to an accurate final solution. Nastran In-CAD contains several element types that are suitable and useful for most industrial applications. There are some which, Nastran can go above and beyond in trying to predict. So it's definitely very powerful and very robust. Now, just a couple of things to keep in mind if you are using elements already, you are running analyses. You want to make sure you use linear order elements for non-linear structural analyses. I know that's a little hard to remember, but try and keep this in mind when you're running non-linear analyses, because most of the time you're likely to obtain more accurate solutions with a fine mesh of linear elements than with a coarse quadratic mesh, even though the quadratic element is presumably supposed to be much more robust and much more powerful. It's useful for certain applications, but not for nonlinear structural analyses. Another thing to keep in mind is when you have areas of high stress concentration, high deformations, you want to make sure you use quadratic elements because they tend to perform better than linear elements. Now, again, all of these rules of thumb and ticks and trips come with their own specific caveats, but as a general rule, these will be applicable.
So, can the software analyze non-homogeneous, non-isotropic materials, things like composites?
Yes.
The short answer is yes.
Short answer is yes.
Another question is, can the solver be ported to run on multiple stations?
No.
I believe that is a negatory. Something on the roadmap is to be able to run this thing on the cloud.
Yeah.
I know that's on Autodesk's roadmap. I don't know when or how soon something like that's going to come out.
Information.
Yeah. Once we do get that information, that's definitely something we'll let everybody know, because running CFD in the cloud is like the coolest thing ever. All right. This is a great question from Jake. What are the main differences between Nastran In-CAD and the built-in stress analysis tool in something like Inventor Professional?
So Inventor Pro is very basic. It can only do linear static analysis in terms of structural analyses. It can only do linear static and modal analyses. Nastran In-CAD, on the other hand, can do
a lot of stuff. And one of the big ones is thermal.
All these different things, right? Inventor Stress Analysis has two of these options. So it's definitely a lot more powerful than Inventor, even though it sits inside Inventor, looks a little bit like Inventor. It's infinitely more powerful than Inventor Stress Analysis.
Definitely. And in regards to In-CAD versus Inventor, the big one that I always hear is thermal. People are always saying, can I do thermal in Inventor analysis? And people used to have to get things like simulation mechanical. But now that's not the case. You can do some thermal analyses in Nastran In-CAD directly into Inventor. It's a great question too from Ian. How can we locally refine a mesh? So that's when we get into things in the mesh settings themselves.
Yep. So local refinement is right here, the mesh control button. So if, say, you wanted to use, let's say you want to refine the mesh along this edge, just select this edge, change the element size, use the number of elements, whatever you want. So I think it was 1.5 to begin with, so I can make the 0.5 if I want to. Hit OK, and then I'll have to regenerate the mesh, but that's how you would do it locally.
Yeah, the other ways to do it is to make this a multi-body solid.
Yep.
And then to apply a different mesh setting to that body. So you would have like part 1 there, and then you might have part 2.
Yep.
That's maybe a small cylinder around that hole.
Yep.
And then you would apply different mesh settings to that cylinder, maybe make them smaller. It really depends, localizing your mesh where you want to do it. And there's a couple ways to do it. And Nikhil showed one. I mentioned another way. There's probably like 10 more ways to do it.
Exactly.
So definitely, if you have any questions about that in the future, reach out to us. Just real quick before we end today, Nastran In-CAD, it's literally In-CAD. That's why the In-CAD's on the end of the name. Nastran In-CAD was developed a number of years ago, and then Autodesk.
60s.
Exactly.
By NASA. So it does come from a reputable source, and it's something you can trust.
As you can see, like that was pretty easy for Nikhil to do. It's not crazy. You don't need to be a full-blown analyst to be able to run some of these simulations. And we like to think about that as people in the design process run analyses that aren't necessarily like that final super analysis, but just to be able to get your designs better earlier, right? So if you're in the whole design process, you're making multiple iterations of your design, being able to do simple testing in something like Nastran In-CAD, or even, Inventor Professional, some of the simulation in there, could help you get to a better spot faster. So with that, again, thank you everybody for joining us today for today's Autodesk Virtual Academy. Nikhil, thank you for joining us both as like a team and both as on Autodesk Virtual Academy today. It's definitely really, really
Yeah, it's been great.
awesome.
Thank you all for attending.